This week you should start looking at section 1.4 of your textbook, which discusses algorithmic complexity, which we'll start talking about next week. For homework, you're going to be working with linked list mutators in the file mylinked2.java. Let me pull that up in Eclipse. I've commented out all the tests except the test for delete, and you can see I'm failing a bunch of tests. That's fine. I wanted to point out one thing that's important about this file, which is that I am redundantly storing the length of the list in with the list itself. So whenever you update, add, or remove an item from a list, it's important that you update in. Let me just show you what happens if I don't do that. I might have a solution. Obviously, this is not fully correct, but this is a solution to the delete problem. What we're supposed to do in delete, you can see here, is to delete the corresponding element. So here it says we want to delete the item at index 1. That would be 21. So I'm expecting the result list to lack that. Of course, I haven't implemented anything, so none of that's working. But you can sort of see what we're expected to do. So if we delete the last item of the list, in this case the third index, then it should be removed. I'm going to try and write this bit of code expecting that I can pass at least one test, which is that when I have just one element in the list and I want to delete it, well then all I need to do is set first to null. That should work. Let's see what happens when I run. You'll see that I'm still failing the test, but now I'm failing with a different error. The error says that in is 1, but there are 0 nodes. What this is telling you is that the counter in and the actual number of nodes are not aligned. So what I need to do is update the variable in at the same time that I update the first pointer. And when I do that, I will now pass the test. Note that that test is now passing. All right. So be careful to update or modify in whenever you modify your list. Let's look at the rest of the problems in this homework. If you run the file with all the tests running, you'll get an output like this. Delete is not working as expected, of course. Neither is reverse, neither is remove. What are these supposed to do? Well, you can look at the output of the test and figure it out. Reverse, if we give it a list of 2 elements, should give us the list in the opposite order. If we have 3 elements, we should get the 3 elements in the reverse order. If we have 4 elements, we should get those 4. If we have 5, we should get those 5. Okay, so reverse is meant to reverse the list. You're not supposed to change the item in any node. You may, however, change the next field in any node. You may also, of course, change first. You can change first in all of these methods. In the remove method, we're being asked to remove all occurrences of an item from a list. So what does that look like? Well, here's some examples. If I have a list with 1 5 and I remove all the 5s, well, the 5 should be gone. That doesn't matter what position it's in, it should go away. And this should work also with multiple 5s. So if 5 occurs multiple times in the list, it should go away. Here's a sort of general example you might look at. I have a bunch of 5s interspersed all over the place, and I'm just removing all of them. It's very important you start thinking about all of these functions before you code, and that's particularly true of remove. I want to get you started thinking about this function. Suppose I'm working in this example list, and I've gotten to the point where I'm about to look at this 5. What do I need to know about the previous list? Well, I should know something that most of the 5s are gone. I'm going to make a special case for the first element, just because the first element is always special in a linked list of the style we've encoded. The first element is pointed to by first. All of the rest of the elements are pointed to by a next pointer. So let's just ignore the first element for now. You guys can figure that out later. But let's see what we should have at this point then. We should have a list where all of those 5s prior to the 21 have been removed, with the possible exception of the first one. And here I am looking at this 5. Now the question is, what do I do to remove this 5? Let's suppose my induction variable x is pointing to this node. Well, then how can I remove it? It's tempting to try something like x gets x dot next, but note that that won't actually change my list. All that's going to do is move my x cursor forward to the object with 31. So how do I remove this node? Well, if I've already got my induction variable here, then I've gone too far. It's important that I stay back. So in order to remove this 5, it's important that my induction variable is pointing to 21 and not 5. What I can do at that point is modify not x, but x dot next. And this will cause 21 to change what it points to. What do I want it to point to? Well, I want it to point to 31. So what is that? That's not x next. That would be x next next. So I want to update my next pointer to the element 2 nodes removed. That will have the effect of taking 5 out of the list. Note my cursor then is in the correct place for me to look at the next item, which is 31. In this case, 31 does not need to be removed. At that point, I can advance my cursor to look at the next element, which is indeed a 5. Note that the pattern here is to always hang back 1. In a linked list structure where you want to mutate, you're always looking not at x item, but at x next item. Because in order to remove something, I need the pointer to the previous element. So I'm going to keep my pointer back as I go through this list. Thus, you'll see there's 2 ways to make progress. Either I simply move x forward, or I can simply remove the next item. Either of these makes progress. Remove the next item, or advance x. Try working on a few more examples before you start coding. With loops in general, it's important to start in the middle, then worry about the end, and only after you've finished those things, worry about how you're going to start your loop. This is particularly important with linked structures. With linked structures, the middle case will do a lot for you, but you often have a special case at the beginning. It's important not to get too worried about that beginning special case right up front. I've ordered the tests to encourage you to work this way. Note that my tests don't look immediately at the beginning of the list. Only after looking at the list in the middle and at the end do we actually go to look at the beginning. I encourage you to code that way. You'll be much more productive.